Hello there, Mr. Sutton here, bringing you the Algebra 2 2-4 lesson on modeling with quadratic functions. In this one, we will be writing equations of quadratic functions using vertices, points, x-intercepts, pretty much anything we can get our hands on graphically. And we will also be finding quadratic models, regression models, given a set of data. For our first example, we're going to dive right into a real-life kind of problem. So we have a graph showing the parabolic path of a performer who gets shot out of a cannon. That sounds like fun. And y is the height, and x is the horizontal distance traveled. So this is actually a picture of the person flying through the air here. And then we're told that they land in a net that's 90 feet from the cannon. Based off of that, we want to write an equation for the height of the performer. So when you're trying to come up with a model, first off, it's a parabola, so a quadratic model would work well. You're going to want to pick the form of a parabola that most fits the information they're giving you. So in this case, we see that we have the vertex and one other point. So vertex form works pretty well when you have the vertex and another point. So let's go ahead and start by just writing our vertex form and replacing the h and k with the vertex. So in general, we have y equals a times x minus h squared plus k. And then replacing that with our vertex, we have an h value, an x value of the vertex of 50, and then 35 for our k value. So we have a x minus 50 squared plus 35. And at this point, we still need to figure out this missing a value. So the way we're going to deal with that is we're going to have to plug in something for x and y. But what could we plug in for that? Well, it turns out they gave us another point that's not the vertex right here that we can plug in. So that'll be our next step. Replace the x and the y with another point that they gave us, and then use that to solve for a. And then just kind of thinking ahead a few steps, once you've got a, plug it back into this expression right here. And that'll give you your final equation. So pause the video and see if you can finish off this one with the instructions we said there. All right, so for x, I'm going to use the 0 from this 0, 15. And for y, I'm going to use the 15 from that point that they gave me. So I've got 15 equals a times 0 minus 50 squared plus 35. And now to solve this, let's simplify this 0 minus 50 squared business. That's negative 50 squared, which is 2,500. So we have 2,500a plus 35 over there. Now to get a, I just need to subtract the 35, which gives me negative 20, and then divide by this 2,500. So negative 20 over 2,500 is my a value, which if I want, I could simplify that. Let's see, we could make this 2 over 250 or 1 over 125. So negative 1 over 125. So plugging that actually back into what we have up here with this y equals, we're going to end up with y equals negative 1 over 125, parentheses, x minus 50 squared, all that plus 35. For this next one, we have a meteorologist who creates a parabola to predict weather tomorrow. Is it going to be lightning or sun? I don't know. I guess this will tell us. X is the number of hours after midnight, and y is going to be our temperature in degrees Celsius. So I'm basically going to have no idea what the answer is because I think in Fahrenheit, but hey, whatever. So we want to write a model that models this over time. Okay, so same kind of idea. Pick a good formula based off the information that they're giving us here. On this one, we don't have the vertex anymore. We do, however, have the two x-intercepts. And it just so happens that there is an intercept form of a parabola that we've learned about. So I think it would be a great idea on this one to write the intercept form and then replace the p and the q in that with the x-intercepts. So see if you can review what intercept form looks like and pause the video. And basically same steps as the last one, right? Replace the things that they gave you in the graph in your formula. That'll give you something with an x and a y in it. And then replace the x and the y with the point that they gave you. Find a, plug it back in, give it a shot. All right, let's see how that went. So our formula for intercept form, that's going to be a times x minus p, x minus q. P and q are just the x-intercepts from the graph. So 4 and 24, and it doesn't really matter which one is which. Now, just like we were saying, we need to replace the x's and the y with whatever other point they gave us, and then solve for this a value. So let's see here. We've got y, I'll call that 9.6 from this y-intercept here. And then we've got a times 0 minus 4, 0 minus 24. And I don't want to leave you with the impression that this is always going to be 0 for x. That just happens to be the x value that we had on the point for these two examples. So plugging that in, we've got negative 4 times negative 24, which is 96, so 96a. Dividing both sides by 96, that's going to be, let's see here, that would be, I guess, 0.1. This would be like 96 divided by 960 if you move the decimal, so 1/10 or 0.1a. Plugging that back in now to get our final answer, we have y equals 0.1 or 1/10, and then x minus 4, x minus 24. For our final example problem here, we've got this big old table, and what's in this table? Well, we have some fuel efficiencies of a vehicle at different speeds. We want to write a function that models this data and then use that model to approximate the best gas mileage. So this could actually be a useful real-life problem where it's like, hey, how fast do I have to drive to get the most miles to the gallon, right? Because who wants to pay for gas? So this is something we're going to do using Desmos. To start this off, I'll just give a couple quick instructions here. You're going to want to go on Desmos and plot this data. There's a little plus you can use to create a table there. Once you've plotted it, you're going to press the Zoom Fit button just to get a good picture of it. That's this little magnifying glass with a plus here. And then after that, you can press the regression button, which looks like basically a line going through a bunch of points. And there's a drop-down menu you're going to see. You're going to want to choose the quadratic regression. It's defaulted to linear. You're going to want to pick quadratic. And then that'll give you an equation that you can write out here. So if you know what you're doing, then pause the video and feel free to give it a shot. Otherwise, you can follow along and you and I will do it together. All right, so here we are on Desmos about to do this problem. Here is that plus I was talking about that lets you add a table. So we're just going to go through and enter all these values in there. So 20, 24, 30, 36, 40, 45, 50, 56, 60, and 70. And then we'll do the y values. 14.5, 17.5, 21.2, 23.7, 25.2, 25.8 gets repeated. And then we got 25.1, 24, and then 19.5. So once we've got all these in there, here's that magnifying glass I was talking about, Zoom Fit. That gives us a nice little look at the data. Definitely looks quadratic. So this is basically the same thing as we were doing when we found a line of best fit, but now this is a parabola of best fit. Speaking of best fit, here's the regression button up here. So we click that to add a regression. And the default, as I mentioned, is a linear regression, but clearly a line is not the best model for this. So if we scroll down, we see we have all sorts of options. We can choose linear, or we could choose, well, any of these. Quadratic, though, is going to be the best fit for this one. So that gives us this equation here, negative 0.014 if I round it off, x squared plus 1.366x minus 7.144 is as many decimals as you want to take that out to. So there was our picture, there was our line of best fit. And you can do all sorts of things with this function. I mean, we could figure out if I plug in a value that was not in this table, what the miles per gallon would be. Like, let's say I wanted to drive 55 miles an hour and figure out the miles per gallon. I could plug that into this function. But now, one thing they actually did ask us to do was to use this model to approximate the best gas mileage. So we're essentially asking the best gas mileage is going to be like the highest y value. So we're asking for the maximum of this graph, which is at the very top here. Now, if we go to Desmos, it turns out that we can just click on the max value of a parabola and it'll tell it to us. It's just kind of like it knows we want to know it. It's this 48.457 and some change, and then 25.9 571. So putting all that together, so this is what I was talking about. You can click the max to find it on Desmos. We saw that our best mileage was roughly 26.0 if we round that off. And that happened at roughly, what did they say here? It was at about 48 miles per hour, 48.5 miles per hour. So good to know. And that's according to this table. I don't know if that's true for a real car. That's just this one vehicle. I mean, who knows? So that's it for this lesson on quadratic models. What goes up must come down, and what begins must end. So this is the end. Hope you enjoyed it. Till next time, Mr. Sutton signing off.